My dear friends, welcome to Rajashekhar classes on applied data science with Python. This is lecture number 567. In this lecture, I will continue my discussion on optimizers hill descent. Before understanding this lecture, I request you to go through my previous lecture, that is lecture number 566. So, simple SGD or mini batch SGD could get stuck. It does not always get stuck, but it may get stuck at a saddle point if you just employ mini batch SGD. And hence we employ some advanced technique to avoid the problem of getting stuck at saddle point. There is an other very interesting definition called convex function and non-convex function. We discussed this slightly when we discussed optimization. Let me just redefine this. Suppose if I have, let me say, if I have a function like this, what is this? This is my, on x-axis, let me say this is my w, isn't it? What is on y-axis? Let me say this is my L of w. Suppose this is how my plot looks like. Yes, this is called, this particular function, let me treat this one as region 1. Which one is region 1? This entire thing, this which one, let me say like this. Yes, this part is region 1. Let me say this part is region 1. Outside this is region 1. Outside this one, this is, let me say this is region 2. Yes, this particular curve is dividing this entire thing into two regions. Inside this one is region 1, outside this one is, let me say, region 2. How many regions do we have here? We have two regions. This function, this is called convex region. If you take any 2 points if you take, let me say, if you take any 2 points in a region, if you take points here, let me assume I am taking 2 points. These 2 points, where are these 2 points? Are in this point and this point. They are in which region? Region 1, isn't it? If you take any 2 points here, if you connect them through straight line, just let me connect it through straight line. Yes, if you connect them through straight line, if all the points which are there on the line lies in same region, then it is called convex function. Just see, if I join these 2 points, this is the resulting line. Every point on this particular line lies in the same region, that is in region 1, isn't it? They are in the same region. Therefore, I can say this particular function is convex function. Let me draw a non-convex function. Let me say so you can let me draw a non-convex function so that you can understand. Suppose I have my w on x-axis, on y-axis I have my L of w here. Suppose if I function like this, what is this region 1? This is region 1, this is region 2. Just this particular curve is, this particular function is dividing this region into two regions. Let me say, let me take any two arbitrary points. I am taking 2 points in region 1. Let me say this is first point, this is second point. They are in region 1. If I join these 2 points, if I take all the points in this line, this portion is outside the region. This portion is outside region 1. Isn't it? Is it not outside the region 1? Therefore, as it is outside the region 1, this particular function is called, what is this particular function? Is a non-convex function. Just see, what is this? This is non-convex function. Isn't it? Just you can compare convex and non-convex functions. This is the example for this one is example for convex function, this is an example for non-convex function. Simple. If you take any two arbitrary points in this particular region, join them, that resulting line lies entirely inside this region. Here if I take two arbitrary points, if I join them, some portion is outside of this particular region. Therefore, this particular function is non-convex function. Convex functions have only one minima. Yes, convex functions have only one minima or one maxima. For example, take this function. There is only one minima and there is no maxima for this, isn't it? We already discussed this one. And the other hand, I can draw a function like this. This function has one maxima. This function has one maximum here. It does not have. Where it is having maxima? Just see, this function has maxima here, isn't it? Therefore, one maxima and does not have minima. Means it's keep on coming like this. There is no minima. Actually, this is keep on coming. This is keep on coming like this, isn't it? Therefore, I can say this function has one maximum. Here, it does not have local minima on the other hand, isn't it? If you have non-convex function, if you have non-convex function, what happens? For convex function, your local minima is equal to global minima. This is important. This is for which function? For convex function. You simply have one minima or one maxima for convex functions. For non-convex functions like this, what is this? This is non-convex function. For non-convex functions like this, you can have multiple local. You can have multiple local minima. Of course, there is only one global minima, but you could have multiple local minima. There is always only one global minima anyway. So that's the fundamental difference between convex and non-convex functions. Very, very important thing for you is your logistic regression and linear regression, even support vector missions, even SVMs, all of them, in all these cases, the loss function we have that we are optimizing for can be shown to a convex function, isn't it? I will repeat. Very important thing for you is your logistic regression and linear regression, even support vector missions, all of them, in all these cases, the loss function we have that we are optimizing for can be shown to a convex function, which means if you find local minima for logistic regression, linear regression or SVM, we can prove mathematically the loss function is convex, and hence for all of them the local minimum is same as global minima. The important part here is for deep learning algorithms like multi-layer perceptrons, they are shown to be non-convex loss functions. In the case of deep learning, except in the case of logistic regression, which is a special case of deep learning, which is literally with one neuron, which is logistic regression is literally with one neuron with sigmoid activation function, which is actually not deep. Logistic regression is not actually deep, is not deep, isn't it? If you have two-layer neural networks, not just a single neuron, but even two layers neural network, the loss function that you get is non-convex loss function. Means you can have local minima, saddle point, isn't it? You can have local minima, local maxima, saddle point, and you can have multiple local minima. Once you have local minima, you can get stuck at local minima, isn't it? Once if you have local minima, you may get stuck at local minima. Suppose you are trying to solve deep learning problem. Let's assume my loss function looks like this. Suppose this is my let me say this is my initial weight. Let me say this W naught. This W naught is my initial weight. Just this W naught is my initial weight. This is my W naught. I can I come here. Just see, I am at W naught. If my I came here from W naught. If I applying gradient descent, I will come here again. I will come here. I will come here. Here, what happens? I came here and I will get stuck. Here this will be get stuck. Why? Because here your tangent derivative is 0. Derivative is 0 means there is no change in old value and new value, isn't it? How it works? Just see. Yes. What is this? If I start initialization at this point, if I keep on applying gradient descent by using this formula, I will move from W0 to W1, W1 to W2. After some stage, I will move to W3. At W3, gradient equals 0. That is derivative equals 0. What is your update equation? Wkij new equal to Wkij old minus eta into dou L. This particular derivative becomes 0. This is 0 means there is no difference between old value and new value. So you can say it is converged, isn't it? That's what it says. Here, I came here, I stuck because gradient becomes 0 here. I am stuck at W3. I am stuck at W3. It is local minima. What I got here is local minima. What I got here is local minima, while the global minima is somewhere. Let me say this is my global minima. You are stuck at local minima. Let me say this is global minima, but your global minima is somewhere, isn't it? Which I can never reach. I never come out of. I never come out of this particular this one. I never come out. I cannot climb, isn't it? I can stuck here. I cannot climb here. This is gradient descent. Here I cannot climb. I am stuck at local minima. That is my biggest problem, isn't it? I can't climb up. It is dependent on initialization. Actually, I am stuck at local minima. It is dependent on initialization. Suppose if I start some other point, let me say if I start W0 here, isn't it? Let me say if I start here, what's happened? Here again I will come here, I will come here, again I will stuck here. Again same justification, derivative is 0, isn't it? Again if I take initialization somewhere here, just I am starting. This is third case. In first case I started initialization here, I get stuck here. In second case I start initialization here, I get stuck here. In third case I start initialization here, keep on coming by applying gradient descent, I will stuck here. Isn't it? Just you are getting stuck at that may be local minima, that may be saddle point. It depends. I can't club. It depends on initialization. Suppose if I start, I can say if I take initialization initialization as we are discussing 3 cases, what happens in these 3 cases? Your W new equal to W old. In these 3 cases, here your derivative becomes 0 and your Wkij new equal to Wkij old. If I start some point, some point here, it will go. What happens? It depending on point where if I start here, again it will come back, come. It will stuck here, isn't it? So in deep learning, what happens here is because it is non-convex loss function, there are multiple local minima based on initial values of W. Based on initial values of W, you could land up at a different minima. So what we have seen here is a 2D case. I will start 3D case in my next lecture, that is lecture number 568. Just go through this lecture. If you have any difficulty, please keep a comment. Thank you very much.